Okay, so what we have here is we have two cars, a car on the left, car A, and then a car on the right called car B. So this is A right here, and then this is B is up here right there. Okay, so this is a physics momentum problem. Okay, so what's going to happen is car A, which is right above here, is going to go and it's moving at some velocity v. I don't know what that velocity is. Car B over here is sitting at a red light, and so it stopped. Its velocity, of course, is 0. And then right here, this velocity here is going to car A is going to hit car B. They're going to become one mass. They're going to like link up. They're going to become one mass, and then they're going to skid. They're going to skid 7.15 meters until they stop. So car A is going, boom, it's going to hit it. They're going to link up, and then they're going to skid together at 7.1 for a distance of 7.15 meters. So the problem is, what is the initial velocity of A that can cause this chain of events to occur? Okay, all right. So let's erase this. And so what we're going to do here is we're going to use momentum. We're going to use the conservation of momentum. The reason you can't use that, you might be thinking, well, let's use energy. The conservation of energy. The problem is once A hits B, it's going to lose some energy, okay? Because there's like it hits it. There's like friction. There's heat. There's sound. Maybe other losses. So when A hits B, it loses some energy. And it loses it, like I said, to other sources. So you can't actually use the conservation of energy here. If it didn't lose energy, then yes, then you could use energy to figure out how far it went. But because there is energy loss, you can't actually use the conservation of energy. Okay, so instead we're going to use a conservation of momentum. And so what that basically says is if I have some object here, and I have some object here, and they're moving, and they hit each other, we'll call this B as before, and then this is A after. And then let's say now this object is going this direction, and this object is going in this direction. What you can do is you can check the momentum of the entire system. And so momentum is just mass times velocity. So this guy has a mass and a velocity. He has a mass and a velocity. And so you can get the momentum of this guy, the momentum of this guy, and then you can add them together and get the total momentum, which we'll call P. We'll call P1, like as in before. And so this is the total momentum of the system. The system is the things that are about to collide. And then after A is after, and so now these things are, maybe they're stuck together or maybe they're moving apart. It doesn't really matter. But the difference is now take this momentum and add them together. We'll call that P2. P1 will equal P2. So the momentum before will equal the momentum after. So energy, you can't say, oh, it had this much kinetic energy total before and this much energy after, kinetic energy after. No, you can't do that because, like I said, you're going to lose some energy due to heat and sound, et cetera, et cetera. But momentum is conserved. So what you can do is you can look before a collision, check the momentum of the system, check the momentum after the collision, and those should be equal, right? And then you can just solve an equation. Now the only time they're not equal is if, like, during the collision there's some like external force out here and it like pushes something. Maybe it pushes this object and makes it go faster. So if there's like some external thing external to the system and it sort of like interferes with the collision, an external force, then obviously then the conservation of momentum does not apply. But as long as these two things are acting independently before and after, meaning there's nothing else interfering with the collision, then you can use the law of conservation of momentum. Okay, so that's what we're going to do. And so what we have to do basically is we're going to check the momentum before and then check the momentum after. All right, so we're going to say of A, mv, and we'll call this V1. V1 is A, the velocity of A. And then we'll say plus, and then we'll do the mass times the velocity here. Now the velocity of B is actually 0. right? So the mass, and you can see the masses here at the bottom, 1,500 kilograms for A, 1,900 kilograms for B, and you can see this mu sub K here, which is the coefficient of kinetic friction, which is 0.65. Okay, so this is the momentum of the system before. We'll call that like P1. So this is just 0, right? So mass of B. So M is the mass of B times the velocity, which is 0. So he has no momentum. But A does have momentum, right? So he's 1,500 kilograms times its velocity. Do I know what its velocity is? No, V1. And that equals, over here, we'll say P2, the total momentum of the system after. So P1 is the momentum before the collision, and P2 is the momentum after the collision. Okay, so so basically what we're going to do is we're going to, because the two cars are together, we can just add their masses, right? So you can say 1,500 plus 1,900, right? That's a 1,900 times, and now these two things are together, and then of course they're moving at the same speed because they're together, and we'll call that speed V2, or that velocity V2. Okay, great. So then we can just sort of simplify this a little bit more. We can say 1,500 V1 is equal to 3,400 V2. Perfect. Now what we're looking for is V1. We're looking for V1. Of course, V2 would be nice as well too. But we really want to. What we really want to know is what's V1. Now, of course, we have an equation here, so let's just solve it. Well, the problem is we have one equation, two unknowns, right? So this is an unknown. This is an unknown. So we need at least obviously two equations in order to solve this. So we need another equation. So what can we do? Okay, so what we can do is we can think about this logically. So V2 is actually the speed right after the collision, right? So the collision happened, and now V2 is now that's the speed of, or that's the velocity of this new mass, of the 3,400 kilogram mass. That's its new mass. So what we can do is we can create a little graph here, right? And we can say the velocity in X, because we're moving back and forth, right? We're moving horizontally, so we're in the x coordinate. So it's going to start off at V2, whatever that speed is. I don't know what it is, and it's going to go for some time t. So on the x-axis here we have time, and on the y-axis we have velocity. So what we can do here is we can say, okay, there's going to be some slope, which is acceleration, right? If you have a velocity versus time graph, this slope here represents acceleration, right? And then it's going to stop. So it has some V2. It's going to go slower velocity until it finally, at some time t, the velocity is now 0, and then therefore it's stopped. So at time t, that 3,400 kilogram mass has stopped. Now you might be wondering, well, how did I know that this? Well, first of all, you know that the slope is negative because it has to be, because because the velocity is going down, right? So it has to go down. But then the next thing is, well, how do you know it's negative, or not as negative? How do you know that it's linear? Well, it's because there's only one force acting upon the. So when this thing starts moving up here, when he starts, let me just change it to maybe like this right here. When it starts, maybe I'll go green. Or sorry, blue. When it starts here, it's going to go in this direction, right? Like that. And then it's going to stop. And then it's going to stop. But now, is it accelerating faster, or is this, remember, acceleration can mean things are going faster or things are going to go slower. Well, it's going to go slower. But what's causing it to go slower? Friction, right? There's friction between these cars and the ground. So, and that friction is constant, isn't it? Whatever the friction is, it's constant. It's a constant friction. So that frictional force, basically, remember, force is equal to mass times acceleration. So because the friction is going to be constant, that means the acceleration is also going to be constant. So that's how come I know that this slope here is linear, because it's well, because if you took the derivative of this slope, whatever it is, it would be a constant value, right? So remember the velocity versus time graph, like the actual line here, and that slope is the acceleration. Okay, and so it's but I don't know what it is, right? Now there's a couple other things that I do know. I do know that this is a 90-degree angle, and I also know that if you were to integrate the area underneath the velocity versus time graph, that shows you the total distance that it was covered, and that we of course know that once the thing starts moving together as a mass, and then once it stops, it's going to travel a total distance of 7.15 meters. So we do know that. Okay, and of course this is 0 seconds, and then this is time in seconds, and of course this is in meters per second over here, meters per second. Okay, but I don't know the slope. So what I can do is I can use the free body diagram of the car. Okay, so what I'm going to do over here is I'm going to draw a little dot right here that represents the two cars massed together, and I'm going to write all their forces that are acting upon that mass. Okay, so I have mg, or gravity, or weight. The weight of the car is pulling down. I have the normal force, that's the road pushing up, and then I have over here the force of the kinetic force of friction. F is friction, and then K is kinetic. Okay, and it's going in that direction. Now you might be wondering, well, is there a force going in this direction? No, if there was a force going in that direction, then it would be accelerating positively, especially if it was bigger. If it was bigger like that, that means it would be going faster and faster and faster. Remember, because the car is going in this direction, so I need something to pull it in the opposite direction in order to stop it. And so that's what the friction does. The friction is going the opposite direction of the velocity, right? Because the velocity is in this direction, right? The velocity is in this direction. The velocity is going from left to right. So I need something to slow it down. I need something to make that velocity vector smaller and smaller and smaller and smaller. And what's going to do that? That's the kinetic friction force. That's going to make the velocity vector go smaller. Okay, so what is mg? Well, mg is the mass, which is 3,400 kilograms, times g, 9.18. And so then that equals 33,320 newtons. Okay. Now, because this car is not moving up or down, it's not moving in the vertical direction, that means also the normal force is also the same as is the same as a weight, because the sum of the forces in y is 0, because it's not accelerating. Remember Newton's first law: if the sum of the forces are the same, no acceleration, and it's not accelerating up or down. It's only accelerating in the in the back and forth or x direction. Okay, so normal is the same as mg, which is 33,320 newtons. Great. And then the kinetic friction, of course, you may remember, is just mu sub k. That's the coefficient of kinetic friction times the normal force. So up here at the top, it says it's 0. Right here, that's the kinetic friction, the coefficient 0.65. So I do 0.65 times the normal force, 33,320, and I should get the force of kinetic friction is 21,658 newtons. Okay, great. But that's the force. That's the force of friction, but I don't know its acceleration. Remember over here, this graph I have velocity versus time, and the line represents, or that slope represents acceleration, but I don't have acceleration. I have the force. Okay, now you may remember from Newton's second law, and we're moving, remember, it back and forth in the x direction. So we can say the sum of the forces in x is equal to mass times acceleration, because we're acceleration in x too, sure. Because we're moving in x. Okay, so what are the sum of the forces in x? Well, we only have one force in x, right? Which is this. The other forces, this one and this one, are in y. Okay, are in y. So, and then that force is negative, right? Because it's pointing to the left. So if a vector is pointing to the right, we're going to call that positive. If a vector is pointing to the left, we're going to call that negative. So this is actually a negative 21,658. That's the forces in X is equal to mass, which is 3,400 kilograms, 3,400 kilograms. And of course, acceleration is what we're looking for, right? AX. So we just divide by 3,400. Boom, boom, get rid of that. And then therefore, acceleration in X is negative 6.37. Okay. So then I can take that and plug that back into this, plug that back into this. And so that line is actually sloped down at negative 6.37. Okay, great. Now that's its slope. But the equation of the line, let's say I want the actual equation, meaning if I want to know what the velocity is at some time t, well, I can say that the velocity in x at some time t is equal to negative 6.37 t, right? So at t means seconds, right? So for example, at 1 second, it's 1 times negative 6.37 at basically negative 6 meters per second. At 2 seconds, t, 2, that's basically 2 times 6, which is essentially negative 12 meters per second, et cetera, okay? But this thing has a y-intercept, and the y-intercept is v2, right? v2, okay. So the equation of this line here, the velocity in x as a function of time is negative 6.37, which remember the negative 6.37 comes from the acceleration, which comes from the forces, which comes from friction. Okay, so it all ties together. Okay, so remember up here we have a formula. Let's actually one of our equations. Let's write. Maybe I'll just highlight this guy like this. Okay. And I'll write number 1. This is equation number 1, okay? Maybe I'll make this blue, sorry. Okay, now I need another equation. Remember, because I have one equation, 2 unknowns, v1, v2. So can I make another equation? Okay, sure, let's try that. Well, I could take this equation, and I could say the negative 6.37 plus v2, it's going to hit 0, right? It's going to hit 0 at time t, right here, right? This line, the negative 6.3, this line right here, right there. I'm doing a terrible job of writing a line. But that line is going to hit this at this point, okay? When is that? I don't know when it is, but it is going to do it. So I could write another equation. We'll call that 2. And that's negative 6.37 times t plus v2 is going to equal 0. Okay. So if I knew the correct time and I knew the initial velocity, t is the time that's going to hit 0. And if I knew the initial velocity, then I would know when it's 0. 0 is its speed or meters per second. Okay, so that's cool. Right here, so I have another equation, and let's turn this other guy blue. Okay, but the problem is now I have 2 equations and I have 3 unknowns. I have v1, v2, and now t. So I have 3 unknowns, 2 equations. So I'm still not quite there yet. So what I could do is I could create another equation, which is this. Notice there's a triangle down here, right? And so what I could say is that the area, what's the area of a triangle? It's 1/2 base times the height. And then this is a right triangle, right? So 1/2 base times height equals the area. Do I know the area? Yeah, I know it's 7.15. And do I know, so let's just write this down. So 3, this is getting kind of messy, sorry. The area is 7.15. The area of the triangle is 7.15. equals 1/2 times the base. The base is how long is the base, and that's t, times the height. And what's the height? Well, the height is v2. v2, just like that. And let's make this green, and let's make this blue, because why not? So now I have 3 equations, right here, and right here. And the first equation I have v1 and v2. The second equation I have v2 and t. And then the last equation I have t and v2. And now what you could do is you could just use equation 2 and 3 and just solve for t and v2, and then you could go back into v1, or you could just like put all 3 of these equations together and just solve them all at the same time. And so that's what we're gonna do. So if you just put this into any system of equation solver, it'll like Mathematica or whatever, it'll just solve it for you. So, but that's trivial. So, but we have 3 equations, 3 unknowns. And if you do that, if you solve for it, you'll end up getting, I don't know what t, I didn't write it down, the t and v2. It doesn't really matter. That's not what's important. What we're looking for is v1, okay? And so, if you put it into a solver, you'll get v1 is equal to 21.6 meters per second. So that's if you solve this system of equations, all right? Okay, so that's pretty cool. Now, what I want to do is I want to show you a slightly different way of solving this problem. Okay, a slightly different way of solving this problem. So so once again, a quick recap. I did the law of conservation of momentum because the momentum before and the momentum after should be the same, unless something is interfering during some external force is interfering during the collision, which that did not happen. So I can use the law of conservation of momentum, and I got equation 1. And then I used my velocity versus time graph to create a graph of the velocity and the time, and then the acceleration, and then I knew the area under the curve. And then I used, then how did I get acceleration? Well, I used my free body diagram, and then I used Newton's second law to get acceleration. And then once I did that, I had all 3 equations. I could solve them all simultaneously, and then I got my answer. Okay, now what I want to do is show you a slightly different way of solving this problem. Okay, so let's talk about force, the force in x versus distance. Okay, so what force is acting on the object in the x direction? Well, of course we know it's the frictional force, right? It's the frictional force, and the frictional force is applying a 21,000. You may remember from before. It's 21,658. 21,658 newtons of force, and it's applying that over the entire distance d. Okay, over the entire distance d, which happens to be 7.15 meters. 7.15 meters. So 21,658 newtons of force is being applied over 7.15 meters, and you may remember that work is equal to force times distance, of course, right? Now, remember that the force has to be moving in the same direction as the displacement, right? So if the object, let's say the object is here and it's moving in this direction, and the force is moving in this direction, then yeah, you can't just say the force. You have to make sure you have to find the force. Let's say this is the force here. You would have to find its components. You would just go, oh, okay, well, this is its vertical component, and this is its horizontal component, and then you take its horizontal component times the distance, and then you could do it, and then you could find the work. But if the force is, like I said, if it's moving off in some other direction, you can't just say this F times that D, because that doesn't work. You have to find the component of the force times the displacement. It has to be parallel to it, okay? In this case here, friction is actually parallel. The force of friction is parallel to how it's moving, to its displacement. So in this case here, it is just, you are just multiplying. Okay, so if I say 21,658 times 7.15, I can find the area under this rectangle, which is 854. And this is joules. Remember, work Work is like energy, right? It takes energy to do work. Or put another way, work is just transferring energy from like one form to another. So in order to go from kinetic to potential, or potential to chemical, or chemical to nuclear, or whatever, if you're moving energies around, that's what work is doing. Work is just moving energies around. Okay. So this work here, or energy, is 154,854 joules of work. That's what was done by friction. Okay. Now you have to ask yourself, where did this energy come from? So if friction was essentially moving some energy from something into friction, where did the original energy come from? Where did this original 154,854 joules come from? It came from kinetic energy, right? So if we were to draw some like little thing up here, you can imagine maybe like a little bar graph or something, that I had some initial kinetic energy, right? And then that kinetic energy got boiled off slowly until there was no kinetic energy. Okay. But there was think of it like a bank account balance, right? I initially had this much money, and then I started spending money, spending it until the money was gone. And who was spending the money? Friction was spending. As I kept, pulling this thing across, or as the cars kept moving across the ground, the kinetic energy got slower and slower, and as the velocity got smaller, then as the velocity got lower, then the kinetic energy got lower, until it stopped, because there was no more kinetic energy, and it had no potential energy, so the energy is gone. So back to this thing right here. This 154,854 joules. Where did that initially come from? Well, it came from the kinetic energy. So, and if I know the kinetic energy, then I know its velocity. And it's important to remember here, like, what velocity are we talking about? So we're talking about from this point right here, after the collision. So after the collision, right here, I'm drawing with my pen. Okay, this is the point at which the kinetic energy, well, of course, A has kinetic energy initially, right? But I'm talking about after the collision, right? After the collision happened, okay, then after the collision, it now has some amount of kinetic energy, and now it's going to bleed it off. It's going to be bled off by friction until finally it stops. So that's the kinetic energy we're talking about, is the kinetic energy of the mass right after the collision. Okay, so this 154,854 joules, that did come from kinetic energy. And so I can say 154,854 is equal to, and what's kinetic energy? It's 1/2 mv squared. In this case here, v is v2, which is the velocity of the mass after the collision, right? And I can just solve for v2, right? I can just to get rid of that, multiply this times 2, take m, divide by 3,400, which is the mass of the total mass, and then of both cars. And then I could get rid of the square by taking the square root, just like that, and then we have v, or v2. And then I can say v2 is equal to 9.5 meters per second. Okay, 9.5 meters per second. And you may remember from up above, if you know V2 is 9.5 meters per second, which came from the kinetic energy, then you can come up here. Remember, it was 1,500 V1. Remember from the momentum, 1,500 V1 equals, I think it was 3,400 V2. And you know what V2 is. V2 is 9.5. So get rid of that and say times 9.5. And then divide by 1,500. 1,500, get rid of that. And then so V1 is equal to 21.6 meters per second. Okay, and of course it's the same as we got before. So essentially, in both of these cases here, I did use the law of conservation of momentum to solve the problem. But in the top case, I kind of use, like normal kinematics, velocity, time, acceleration, normal kinematics to help solve the problem. But in the second case here, I didn't really use that. In the second case, I use energies. Yeah. So the first case, momentum plus kinematics to solve, and in the second way, I use momentum also, but I use energy also. Momentum plus kinematics in the first one, and momentum plus energy in the second one. And it doesn't really matter which one you use; they both will yield the same answer. But it's good, of course, to understand how the entire system works. Depending on which vantage point you're looking at. So, all right, that's it.